is total. Do we think this function is total? Well, yeah, we believe that r prime has the same length as r, and therefore that this does terminate and gets to the base case no matter what list you start with. But the proof of that is not trivial. It's not the thing that the fixed point checker can check for itself. So we're not allowed to define this function in coq. What do we do instead? I'll show you a way that we can define something that looks like this in coq a little later. But for now, let's do something more primitive. We're going to use the concept of fuel. We're going to say, let's run this recursive function cell sort on L with a natural number n that says, how hard to try? So cell sort Ln is structurally recursive on n. And remember, a fixed point function doesn't have to be structurally recursive on all of its arguments. Any one will do. Any one is enough to prove termination. So if n is the successor of something, then match L with x cons r and do what we really want to do, which is find the smallest element in x cons r, that's y, and then put y at the front and do the recursive call on r prime. But with n prime, the next smaller natural number. So we start with a certain amount of fuel, and each step uses up some fuel. And if we get to the empty list, that's great, because, well, we shouldn't get to the empty list because somebody is calling cell sort with, oh no, that's fine. Cell sort Ln. Oh, this is selection sort, not select. So that's fine. The sort of the empty list is the empty list. That's very good. And here, we're trying to sort this list, and we ran out of fuel. So let's return some arbitrary list. Let's return nil. This is like bogus subtraction in the natural numbers, right? We don't know what to return. We're forced to make a total function, so return something. Nil is certainly not the sort of that cons on the left. So we hope to be using cell sort only in contexts where we have enough fuel. Yes?
Doesn't it make it harder to verify them? Wouldn't it be easier to really make the proper fixed point proof and then have a simpler function to verify?
No, this will be pretty easy to verify because we'll do it by induction on n, and we'll have enough fuel. This will work. It's not going to be a problem. All right, so let's do cell sort of 31415 with fuel 3. And if we simplify this, you notice that we got a sorted list, 113, and then it ran out of fuel, so it returned nil. And that's not equal to the other list, which is 11345, which is easy to prove by inversion. Okay? What if we have too much gas? Let's sort 31415 with too much fuel, with 10. So when we simplify, we get what we wanted. Too much fuel is not a problem. And you can see that from the implementation, because once we get to the empty list, here it didn't matter how much fuel we had. Okay. Now let's define selection sort of L as cell sort with fuel length of L. All right, so I claim that's selection sort, and that's correct. So let's sort 31415926535, and that's cell sort on that list, but with length of whatever. And if we simple, we see that it seems to have worked. Okay. So we want to prove that the output of selection sort is sorted and that it's a permutation of the input. Those are two separate proofs. We'll do each one. What does it mean for something to be sorted? Well, I've written this inductive proposition that says the empty list is sorted and I cons nil is sorted, and IJL is sorted if I is less than or equal to j and JL is sorted. All right. Who believes that is the right is a right specification of non-decreasing order? Because, you know, if we get that wrong, then our proofs aren't too useful. I think it's right. It seems to get the job done. All right, so let's define a predicate on a sorting algorithm. Predicate on a function f from list nat to list nat called is a sorting algorithm is, for all lists AL, f of AL is a permutation of AL, and f of AL is sorted. So that's our specification of correctness for sorting algorithms. And the proposition we want to prove is selection sort correct, which is a sorting algorithm of selection sort. So let's go. Here we go. We want to prove, step 1, that if select XL is this list, the smallest element is Y and the rest of the elements is R, then X cons L is a permutation of Y cons R. Right? That's select perm. It's the proof about the select function. So, how do we prove this? Well, as usual, we do intros. We have two things above the line to do induction on, X and L. We could do induction on either one, but induction on the natural number is probably not going to be useful. So we're going to do induction on L. If I say induction on L right now, a bad thing will happen, which is X will be fixed in all of the inductive cases, and as different things are selected from sublists of L, they all will have to be X. And that's not going to be good. So we need to generalize X. We revert X to move it below the line to make a more general induction hypothesis. And now we can do induction on L. So we'll do induction L. In each case, we'll do intros. We'll simple in star, so simple above the line and below the line. And now we have the nil case, where we have to prove that X is a permutation of X. So that's easy. And here's the cons case. And what do we do now? Well, we have an if statement. So we could just do case analysis on the if statement. B destruct X question mark equal, or less than or equal question mark A. And let's put a bullet here to do this case. Okay, now what? We have these lets that sort of pattern match on a tuple to get the pieces of the tuple. And how do you deal with a let like that, whether it's above the line or below the line? Well, select XL is a pair. It has two components. How do we reason about what the two components of this expression come out to? We do it with destruct. So we could say destruct select XL, and that will break it up into two components, and that's fine. But actually, we'd like to remember that those two components are equal to, that pair is equal to select XL, so we put an equation here called H0. So what's happened here? This is going to be replaced by its two components, which are called L0 and H0. Excuse me, L0 and N. And we get the equation H0 that relates them. And so now L0 and N have been substituted in those let expressions. What were the let expressions? Well, L0 and N are substituted for J and L prime. And that made it possible to simplify the next let expression. And so here we are. We need to prove that if select XL is N comma L0, then this is a permutation. Well, there's an A in both permutations. It's seems promising to get rid of the A. Right? So how do we do that? Perm swap. We could do perm swap. Right? How do we use perm swap though? Because we can't just apply perm swap right now. We have to use the transitivity of permutations as follows. E apply perm trans. Now apply perm swap. And we brought to the A to the front in the first argument of the permutation. So we're going to do it again in the second argument. E apply perm trans. But now in the second subgoal, apply perm swap. And now the A is at the front there, and we can apply perm skip. All right, so this is good. And if we're lucky, the induction hypothesis will work directly. I don't remember if that's true. Apply IHL. No. All right. XL can be made to match if we instantiate X correctly. But YR, well, we have this select XL. So let's do this. Let's specialize IHL with L substituted, with X, with this X substituted for that X. All right, so this is what specialize is going to do. And now we can rewrite by H0 in IHL. Right, because here we have select XL, here we have select XL equals a particular pair, and when we do the rewrite, this particular pair will be substituted for that pair, and things will be nice. So rewrite. And now, this is good because IHL is exactly what we want, and we can say auto. All right, that was the first subgoal. Here's the second subgoal. And we can do basically the same thing. We can destruct, select AL, EQN, colon, question mark H. Question mark H just means pick some name starting with H. So H was already taken, so it picked H0. We could just as well have said EQN colon H0, but then we would have to look above the line and see what's taken already. Okay, what do we do here? Look at the proof goal below the line and figure out what it is we have to do. Let's get rid of X. So we know how to get rid of X. We just cut and paste, copy paste those two lines, and then this line. All right, now what? Now we can use the induction hypothesis. Specialize, IHL. What do we want to use for this X? Well, we want something that matches the select XL. What we have is select AL, so we'll specialize the induction hypothesis with A. And then we can do this, and we're done. Okay, so we have to prove that cell sort is a permutation. How do we prove that cell sort is a permutation? We can do induction. We have two things above the line, N and L. Which do we do induction on? We're going to do induction on N. So, we're going to do induction on the length of the list. You've seen inductions on the size of something. That, I think, will work quite well here. So, it turns out intros was the wrong thing to do because we want to generalize by L. So we could say revert L, and now we can do, no, revert L doesn't work because H depends on L, so we have to revert L and H. But we could have gotten to this point by just saying intro n, right? That's what we're going to want to do. In fact, we can even say induction on n, which will use everything after n as the induction hypothesis. So the clever way to do it is to say induction on n. The boring way is to intros, realize you've introed too much, revert to things you need to revert, and now we can do induction on n, which is the way I would do it, because I've already typed intros. Okay, so then we'll simple and intros in both cases. Okay, so how do we prove that, how do we do this? Well, if the length of L is 0, what do we know about L? It's the empty list. All right, so how do we make that happen? Here's how we make that happen. This is a very common pattern. You'll see it all over the place. Destruct L, and then inversion H. And the cons case will go away because the inversion will destroy it, and the nil case will remain. And so now perm nil solves that one. All right, if the length of L is the successor of n, what do we know about L? It's not nil. How do we do something about that? We do this. We destruct L and inv H. And that makes the nil case go away, and now we've got n0 cons L. In fact, since we're going to just do destruct L inv H in both cases, we can tell in advance that that's going to happen. We'll just do that. Okay, so now we're in this case, and we have to reason about this select n0 from L. So how do we do that? Same as before, destruct select n0 L eqn colon question mark H. Good. Now we have to prove this. Now we have to think. Everything up to here was just typing. Now you have to think. This is unfortunate. Once in a while you have to think. Okay. Hint. We just proved this lemma, that select is a permutation. Right? We just proved that NL0 is a permutation of N0L. So let's remember let's assert H0 colon equals select perm. So assert, there's two ways you can use assert. One is to assert a thing and then prove it, and the other is to assert a proof. Select perm is a proof of something, so that's why there's a colon equal. H0 is the proof select perm, and it's a proof of this. Okay, now we're interested in using H0 on H itself. So we want select perm applied to N0 and L. So let's do that instead. Select perm applied to N0 and L is this. So that's a nice fact above the line, in particular because we can rewrite by H in H0. And now we have this. Okay. So what do we do next? Trans, right. So we'll apply perm trans, and then see if either of the subgoals can be proved by an assumption that's above the line. That's the semicolon. So this will fail in the second, right? This will fail. So what we're going to do instead is try the assumption. So see if either side can be proved by an assumption.